Here's an application of exponential functions where we're going to use a formula involving an exponential function to find accumulated value of an investment. So in this case, it's an investment of $5,000 at an interest rate of 6.5% after 10 years. And we want to calculate the accumulated value in 3 different scenarios. So first, it's if the interest is compounded semi-annually. Now, in this case, we're going to use the formula A for accumulated value equals P, which is the principal, times the quantity 1 plus R over N. This is where R is the interest rate, written as a decimal. N is the number of times per year that the interest is compounded, to the exponent N times T, where T is time. So we need to collect information from the statement of the problem here. So let's go through this. Accumulated value of an investment of $5,000. So this is the original investment. That's the principal, P. So our value of P is $5,000. At an interest rate of 6.5%. So that tells us, I'm going to write some information down here. So we know so far that P is 5,000. Interest rate of 6.5% tells us, okay, so R is 6.5%, which as a decimal, you move the decimal to the left 2 places, 0.065 for our value of R. After 10 years, so time is 10. If the interest is compounded, so now we're looking at our specific scenario. If it's compounded semi-annually, N is the number of times per year that the interest is compounded. So if it's semi-annually, that's twice a year. N equals 2 in this case. So for part A, we would plug in what we know. So this would be 5,000 for P times 1 plus R, which is 0.065, over N, the number of times it's compounded, which is 2, to the N times T. Now when you input this into the calculator, you need to be careful in a couple of places. So you make sure you put parentheses around what's in parentheses here, so that's less of a concern. When you put your exponent, you either should go ahead and multiply. I mean, the calculation here is simple enough, 2 times 10, so let's just call it 20. If this were something that you didn't want to just work out in your head, then you would need parentheses around it if you were going to input this into your calculator. But I would advise you to just input your exponent as 20. And so I'll put this into my calculator real quick so you can check your answer. So if we do 5,000 times 1 plus 0.065 divided by N, which is 2, to the N times T, which is 20, after 10 years, this gives you $9,479.19. Okay, so this is the amount if it's compounded semi-annually. So for part A, your answer is, I want to keep track down here, $9,479.19. Okay, now let's think about what changes for part B. So we're going to keep the same principal, the same interest rate, same amount of time. The only thing that's going to change for part B is it's compounded monthly. So the number of times per year that it's compounded now is 12. So forget N equals 2 now. Let's use N equals 12. And so I'm not going to rewrite this whole expression. I would just change what I need to change. So we're only going to change the value of N. Instead of 2, we're going to use 12. It's compounded 12 times a year. So same thing up here in the exponent. The exponent will be 12 times 10. And so the exponent now is 120. And you might start to feel like, well, this is going to make a huge difference in the accumulated value. But let's see if it really does. So I want to see what the answer to part B is here. So if you put this into your calculator, let's see, so if I just change the n from what we entered last time to 12, then the accumulated value now, instead of this 9,479, we have increased the accumulated value, but not as much as you might expect. $9,560.92. So this was about 480, now we're up to 560, so it's increased by about $80. I'm going to record the answer down here just to keep track. Okay, so when we went from compounding twice a year to compounding 12 times a year, the accumulated value after 10 years increased by about $80. Now what if it's compounded continuously? For continuously compound interest, we use a whole different formula. If it's compounded, if you see this keyword continuously, the formula is A equals P times E to the RT. So if you consider how this formula is different, in a way, I mean, the E is replacing this 1 plus 4 over n. Now the exponent has changed as well. So I'm not getting into precise differences between these functions, but I will say, and you'll see in your notes, that E, the number E, oops, and I almost erased our other answers. E is approximately equal to 2.7, it's around there. And it's equal to, this is a calculus concept, but what's called the limit as n approaches infinity of this expression 1 plus 1 over n raised to the n. So as n, which is the number of times per year that it's compounded, it makes sense that we would have n getting really, really big if we're talking about continuously compound interest. If you're constantly compounding the interest, then the number of times per year would approach infinity. That makes sense. And then if you look at this 1 plus 1 over n, so this is where we used to have in that compound interest formula 1 plus r over n to the nt, it's being replaced by this E, which is equal to this right here. Okay, so like I said, I'm not getting into exact differences, but that gives you a sense of how you get from that P times 1 plus R over N to the NT formula and changing it to this PE to the RT. So we haven't shown it in detail, but maybe that gives you a general sense of what's happening there. Okay, but all you're really expected to do in this problem is just compute the accumulated value. So you don't really have to see the relationship between those formulas. You just have to be ready to use it. So P, the principal, is 5,000 times E, interest rate is 0.065 times T, which is 10. Now, in the previous formula, I was encouraging you guys to go ahead and multiply in your head. And here you can also, times 10, so that's just going to move the decimal over one place. But frequently this product here might be something that you don't really want to do in your head, so let me emphasize again. When you input this into the calculator, if you want all of this to go in the exponent, you should put parentheses around it. So I'm going to input 5,000 times E, which most likely you have to press second or shift and then the ln button on your calculator is most likely how you enter E to some exponent. So in this case, E to the 0.065 times 10 is $9,577 and 70 cents. So this is the answer to part C. And notice again, so this time, the increase was even smaller, going from compounded monthly to compounded continuously. The accumulated value, and keep in mind, this is after 10 years. The accumulated value has a difference of, around $17. So not a huge difference. So I bring that up just so when you're checking your answers, if you're comparing the accumulated value with different values of n, yeah, as n gets bigger, you do expect your accumulated value to get bigger, but not by a lot in most cases. So it should be in the same ballpark, but increasing as n increases.